Alright, so all you people out there who are missing chemistry right now, this one's for you. Let's start going over some of this, okay? What is this answer to this darn question?
Cold is the lack of heat.
Cold is the lack of heat. When you say heat, though, what do you mean?
Energy.
What kind of energy? Kinetic energy. So the lack of kinetic energy yields heat. So, the lack of kinetic energy yields cold. So a lot of kinetic energy essentially means it's heated, right? So let's go through some of these. Let's see where we are here, okay? So what happens when an ice cube is added to a soft drink? Go for it.
Ice cube absorbs the heat from the soft drink.
And?
Can I explain how it works?
Well, yeah. Tell me a little bit more. Like what happens when it absorbs the heat as well?
So the ice cube particles are vibrating pretty slowly, and the soft drink particles are vibrating faster because they're at a higher temperature.
Mm-hmm. So
the faster vibrating particles in the soft drink are colliding with the ice cube, slower particles, making them panic.
So as they collide, what's happening?
They're making the ice cube particles move faster.
So they're transferring their energy, right? So when they collide, they transfer some of that kinetic energy to the slower moving particles so that in the end, they end up with the same energy. So what's happening to the ice as that occurs? It's melting, right? So as they transfer kinetic energy, the solid starts to become more energetic and it starts to melt. Yeah.
How do you observe this?
You can observe it from a macro scale, like the ice literally melting, or you can actually use, I'm not going to say electron microscope, it might be like a TEM transmitting electron microscope or a SEM scanning electron microscope. There's different types of microscopy that can be used to observe these kinetic energy changes, but basically we know that kinetic energy, the average kinetic energy is temperature. We can actually literally use a thermometer to observe the changes, not the actual collisions. But basically, we can cause it to melt via transition or transferring of kinetic energy, right? So, tell me a little bit more. We kind of just worked through this, but what's the rule about how energy is transferred? Go for it. High kinetic energy or temperature to low kinetic energy or temperature. When does it stop? When does it stop transferring? Right, thermal equilibrium. Basically when things are equal, right? So if the ice continued to transition to be warm from the excess kinetic energy, the soda would get technically warmer. No, it doesn't. It actually gets to this place where they're in between the temperatures of the ice and the soda. So it's called equilibrium. Equilibrium is a term we're going to start to use a bit more. True or false? Explain. Explain. How all particles of a substance have the same kinetic energy. Anybody? Go for it.
False, because particles collide with one another at almost different speeds, and kinetic energy is
Right. Okay. So some of them are going to be having a higher speed, higher kinetic energy. Some are going to be having a lower kinetic energy, or just slower. There's a curve on the paper that represents that. I want you to draw yourself this curve. So I'm gonna put one of them like this in green, and one of them in red. What you need? If you want to choose option F, you have to add it to the signature. If you just want to use an add it to the signature. Okay. You got my shells. Go pick up the one here. Okay. So you have this. This is kinetic energy, and this is number of particles. Okay. So this is kinetic energy, number of particles. What do you notice about the green one? What's one big difference between the green graph and the red graph? Okay, but what's higher?
The number of particles.
The number of particles, the y-axis is higher. So there's a higher number of particles here at this kinetic energy, right? What else do you notice is different, Sam? That was really one difference. There's only one other big difference. Jalen?
The red line goes to a higher kinetic energy than the green line.
Okay, so the red line has a higher range of kinetic energies, so it's got a longer range. So if it goes to higher kinetic energy, Sam, back it up. What can you tell me about this substance, the red substance?
It is a gas.
Oh, it could be a gas. Yeah, I'm going to say they're all gases then. So if they're all gases, what's different about this gas if it reaches higher kinetic energy?
It has more collisions.
Could happen. Anybody help them? Searching, just trying to pull on teeth here.
Higher temperature.
It's higher temperature. Okay, so if you reach a higher kinetic energy, it means you have more vibration, so you're really hot, right? So you're a warmer, hot temperature. So this green line, you would say the green line is a cooler temp, and the red line is a warmer temp, right, situation. So you can actually look at a graph, and you can tell me that. Basically, based on the range that Shaylin said, it reaches a higher overall kinetic energy. Yeah.
I guess the higher kinetic energy is really in the spirit of 420, isn't it?
Why? We're getting here. So anyway, the definition we talked about last week was about how kinetic energy, average kinetic energy and temperature in Celsius or Kelvin. Kelvin, we always talk about Kelvin, right, with gases anyway. We said that they were technically equivalent. So temperature is directly related to kinetic energy average. So based on this kind of curve, it's kind of like a bell curve. And a lot of people say, oh, the bell curve represents like A, B, C, D, E, F, like the grades that an average class would have. I don't believe in the bell curve because if you're an A student, everybody can be an A student. Not, I don't have to partition you. But where would the average be on the green graph?
Top.
The peak, right. So the top peak is the average kinetic energy. So the average kinetic energy, I can directly relate average kinetic energy to temperature, right? So let's say this is 25 degrees C. We can convert that to Kelvin if needed. Where's the average kinetic energy on the red line?
Higher.
It's what?
35.
35, okay, I like. So this is going to be its peak right here as well. Let's just call this 35. So you can actually tell that the temperature is higher because the peak is higher. So the average, most people fall in the average category. The highest number of particles is the average kinetic energy, aka temperature of this system. The average highest number of particles is the average of this system. So you always have those super speedy particles. Those are the ones, remember, we were talking about blowing on a soup spoon. Those are the particles you blow away first. It cools down your soup overall. The ones that are chilling in the inside the spoon are these down here. Yeah.
So like the more particles there are, the less kinetic energy.
The overall less kinetic energy, right? Now underneath this green curve and underneath this red curve, there's actually the same number of particles total. But more of the particles are at higher temperature here, more of the particles are at lower temperature here overall. So that's called a Maxwell-Boltzmann curve, but I just want you guys to be able to look at it graphically and to get the same information you could from reading. Okay, so let's go through a couple more here. We were four. What is the definition of temperature? Who got that far? Tanner, you got me?
The average kinetic energy.
Basically, that's it, right? We just went over that. 5. Name 3 kinds of motion. Go for it, Benny.
Translation.
Okay.
Vibration.
And
rotation.
okay. So the vibration is the definition of vibration is wiggle in a fixed position. Okay. Translation and rotation. So there we go. We just did the 3. And so all those can be related to kinetic energy. Which term is applied to a situation in which energy has been transferred from faster particles to slower particles, and as a result, the particles end up traveling at the same speed? Kevin. Thermal equilibrium. Okay, so they're all traveling at the same speed. Their kinetic energy is the same. They're at equilibrium. Okay, so we're going to use that word as we go through this here. Okay, so that was our first part. Second part, you guys can work with a buddy of your choice. Anybody. There are 12. I want you guys to go through the first 12 questions on this yellow sheet, and then we'll be done with our intro, and then you guys will call scavenger hunting.
Can we do that on the same?
You can do it on the same sheet of paper, yes. So I'd say 15 minutes. 15 minutes on this, okay? 15 minutes. Okay. All right, so heats and joules, temperatures in Celsius. So we already know that there are 2 different things, but how are they different? We're going to kind of investigate more. But they're both being heated at 150 joules. And C, which container did the liquid gain more energy? C? 2C? More energy?
Small. more.
Or did they both gain the same? They both gained the same. You just said 150 and 150, right? So they both measured 150 joules, so they were the same in terms of energy. But then D says for which container, include whether the temperature is expected to increase, decrease, or remain the same. So for both of these, the temperature should what? Right, the temperature should increase for both. But then you have a little explanation with this. The saucepan versus the stock pot, they're different volumes of water being heated, right? That different amount of water being heated is going to distribute the heat more evenly, or it's going to distribute the heat differently. So what do you think is going to be different about these two temperatures at the end? Which one's going to have a higher temperature at the very end? Right, so the 4-quart saucepan is going to be of higher temperature than the 8-quart stock pot, which is going to be, its temperature is going to increase, but it's going to increase just a little bit. So they're both getting the same amount of joules, but their temperatures are rising to different heights because of the differences in volumes. Okay, so there's just a distribution problem there. Part 3, so you had all this data to look at, and the reason I want to look at this one today is because you'll notice for homework you just are finishing up revising your experimental design, starting your experimental design, your experiment, whatever it is. Once I've approved it and said, I gave you some tips on things to change, go ahead and start, okay? So one thing I needed to note on was how you always want to change one variable at a time, right? The independent variable is the variable I'm changing. So if I'm watering plants with different liquids or something, then I'm going to change just the type of fluid I'm giving the plant. I'm not going to change the volumes. I'm not going to change the locations. I'm not going to change the amount of sunshine. I'm not changing anything but one variable at a time. But then I could try another experiment within my Big Mythbusters project and go, oh, maybe the different volumes will change the different growth of the plant. So I'm going to use the same fluid, but different volumes. So that's what these 3 experiments are kind of showing. You're changing one variable at a time. It's influencing different variables, different factors. So in 3, what does delta T mean? Change in temperature. So change in temperature is very specific as temperature final minus temperature initial. Write that part down, okay, because we're going to talk about that tomorrow as well. Temperature final minus temperature initial, TF minus TI. 4, which experiment, you guys have read that, 4. Experiment 3, good. So that experiment 3, you had delta T staying the same, everything else was changing. Number 5, experiment 2, that one was the mass was staying the same, but the temperature and energy was changing. So number 6, why was it necessary to perform all 3 experiments? I just talked about that. You need to have one variable changing while everything else is the same. So you can see causation versus correlation. So if I wanted to do an experiment to see how I could gain the most weight, I could either not sleep or I could eat a lot. But if I did both at the same time, how would I know which is causing it? I wouldn't. I'm trying that experiment now. Okay. Okay, 7. Circle either small or larger. For A, when the same amount of energy is applied to the sample of water at different mass, the change in temperature gets smaller as the mass of the water increases. So what you saw was an increase in mass caused a what for temperature? Decrease in temperature. So directly or indirectly? Indirectly. Anytime there's one up and one down, it's indirect. For 8, temperature change and energy required. What was different, or what was the statement you said, Strauss? Okay, so greater energy applied equals greater temperature change. So increase in Q is an increase in delta T, so they're directly related. You can see that. For 10, to get the same amount of temperature change, you will require larger heat for the larger mass of water. That's showing a direct relationship as well. What did I say? Oh, increase in mass at the same temperature change will yield a greater Q. Q is what variable here? Heat. Thank you. Q is heat. Okay, so then you get down to 11. It's talking about what of these things are represented in each of the experiments. We kind of just talked about the direct and indirect relationships. What you can conclude from each of these is that if the variables are on the same side of an equation, they're indirectly related to each other. If the variables are on different sides of the equation, like equals marks, as one side goes up, it equals another thing that goes up. So they're directly related. So what we have is a final equation. Q equals MC, which is not in this little experiment part yet, C delta T. Write down this equation for yourself. This is called the Q equals MCAT equation. Why do you think it's called MCAT?
like a cat.
Looks like a cat. Yeah, see a T, but it's delta T. So everyone say delta T when you say cat, right? Okay, so you'll see that increasing mass will increase Q, increasing T will increase Q, but these two would be indirectly related based on our data from experiment 3 or something, yeah, 3. But this is the one thing we have not talked about yet, and we're going to talk about it tomorrow, but it's called the specific heat capacity, C capacity, that's why it's called C. So the specific heat capacity, the amount of heat required to raise temperature of 1 gram of substance by 1 degree Celsius. So you'll see that this has units of mass, grams, that's why this mass is here. A delta T is going to be in Celsius this time, so that's why the C, degrees Celsius is here. And amount of heat, so heat is in joules, and that's why that's related. So C, remember R constant from gases, R had all those units in it that were relevant to the equation. That's what C does for us this time. But we're going from gases to thermo, and so I'm trying to partition our minds here because we do not talk about Kelvin in thermochemistry. We talk about Celsius. Why? I have no idea. But that is what we do. Usually because most of our thermometers are in Celsius, and most of our heat experiments we can do quantitatively in the lab. Gases, it's hard to measure like their temperature because they're not really a contained system. So, okay, so game plan for the rest. We have 45 minutes, just about how much time I wanted. You guys can, whenever you get done with anything you're working on, drop off the cold and the yellow papers here. If you have missing work, you sit in your desk and you get your missing work done. If you do not have missing work, you're going by a 7-year house. Okay, you need to be in a duo or in a triplet form. Okay, you have one piece of paper you are writing on all your answers. The scavenger hunt papers are here. Go explore. You have to take pictures. You have to, measure things. You have to do a couple of things. Okay, so find somebody or a triplet each way, and you guys can grab one of these and go on an adventure. Be back by 10:27. I want to see you 3 minutes before class ends, okay? If you have missing work, work on your missing work. Otherwise, take a piece of paper with you. Stop writing on mine. Okay, cool. Only one? Don't write on mine.
Yeah.
Okay, so don't write on that paper, write on your paper.
Yeah. Is there something I can do to get these 3 grades up?
1 second. Which